Solving equations and inequalities involving absolute value is another topic in which my students often experience difficulty. This video will explain these concepts. Let's first review the algebraic definition of absolute value. Informally, we know that absolute value makes everything non-negative. But how do we express this idea with algebra notation? For any real number x, the absolute value of x is given by x if x is already non-negative, and by the opposite of x if x is negative. Remember that the variable x can be any real number. To make a negative number positive, we take its opposite. As usual, let's consider a few examples to illustrate this definition. To evaluate the absolute value of minus 17 using the definition, we notice that minus 17 is negative. So it comes out of the absolute value as its opposite. According to the double negative law, this equals 17. Of course, we'd never actually use the definition on this problem because it's easy to make minus 17 positive by changing the sign. To evaluate the absolute value of 3 minus pi, we note that 3 minus pi is negative. So it comes out of the absolute value as the opposite of the quantity 3 minus pi. We can distribute the negative to get minus 3 plus pi and use the definition of subtraction to rewrite as pi minus 3. Therefore, the absolute value of 3 minus pi equals pi minus 3. To evaluate the absolute value of x squared plus 5, we notice that x squared plus 5 is always positive. Therefore, it comes out of the absolute value as itself. The expression absolute value of x plus 3 is harder to evaluate. Since we cannot determine the sign of x plus 3, absolute value of x plus 3 cannot be simplified further. Now let's consider equations and inequalities involving absolute value. We will present a summary of how to address the absolute value in 4 main cases and then provide examples to illustrate. Suppose that x and y are variables and a is a positive real number. Absolute value of x equal a means that x equals plus or minus a. Absolute value of x less than a means that minus a is less than x is less than a. In other words, x is sandwiched between plus and minus a. On the other hand, absolute value of x greater than a means that either x is less than minus a or x is greater than a. In other words, x lives outside of plus and minus a on the number line. Absolute value of x equal absolute value of y means that either x equals y or x equals the opposite of y. In other words, x and y are either equals or opposites. Note that both situations with strict inequalities are still true when using less than or equal or greater than or equal. We will now consider 5 examples using these properties. First, let's solve absolute value of 2x minus 1 equal 5. We start with the given equation. We need to remove the absolute value before proceeding to solve. To have an absolute value equaling 5, either 2x minus 1 is 5 or 2x minus 1 is negative 5. Now we add 1 on both sides of both equations, and then divide by 2 on both sides of both equations to get that x equals 3 or x equals negative 2. We can plug these values into the original equation to see that they both check. When x equals 3, we get absolute value of 5 equals 5. And when x is negative 2, we get that absolute value of negative 5 equals 5. Now let's solve the absolute value of 3x plus 4 less than or equal to 6. We begin our solution with the given inequality. We have an absolute value inequality with less than. So the stuff inside the absolute value will be sandwiched between plus and minus 6. Removing the absolute value, we get that minus 6 is less than or equal to 3x plus 4 is less than or equal to 6. We can subtract 4 across the compound inequality to get negative 10 less than or equal to 3x less than or equal to 2. Then we can divide by a positive 3 to get negative 10/3 less than or equal to x less than or equal to 2/3. This represents the solution in inequality notation. We are often asked to graph the solution and or write it in interval notation. I find that graphing the solution often helps to correctly write it in interval notation. We use closed circles on the graph and square brackets in the interval notation to indicate that we include the endpoints in the solution. For our third example, let's solve absolute value of 5x minus 3 greater than 2. We begin with the given inequality and note that we have an absolute value inequality with greater than. So the stuff in absolute value lies outside of plus and minus 2. We get that either 5x minus 3 is less than negative 2 or 5x plus 3 is greater than 2, and we have two inequalities to solve. We add 3 on both sides of both inequalities and then divide both inequalities by positive 5. Luckily, when we multiply or divide inequalities by positive quantities, the inequality sign is not effective. Therefore, we get that x is less than 1/5 or x is greater than 1. The graph of this solution has the areas outside of 1/5 and 1 shaded with open circles to denote that the endpoints are not included. In interval notation, we have to use a union to describe the solution and open parentheses to denote that the endpoints are excluded. Recall that we always use parentheses and never brackets with either infinity symbol. Now let's consider another example in which the absolute value expression is not isolated. We begin with the given inequality that the absolute value of 3 minus 2x plus 4 is greater than or equal to 9. The only situations we know how to handle have the absolute value isolated on one side of the inequality. Thus, it seems reasonable to subtract 4 from both sides of the inequality. Now we have an absolute value greater than inequality that we can address. Removing the absolute value, we get that our stuff is either less than or equal to negative 5 or greater than or equal to 5. We can subtract 3 from both sides of both inequalities. Now we want to divide both inequalities by negative 2, so the inequality signs will reverse upon the division. We get that x is greater than or equal to 4, or x is less than or equal to minus 1. We graph this solution set by shading everything outside of negative 1 and 4 with closed circles to indicate inclusion of the endpoints at negative 1 and 4. The interval notation has closed brackets at -1 and 4, but parentheses at plus and minus infinity. For our final example, let's solve absolute value of x plus 3 equal absolute value of 2x minus 7. We start with the given equation. For two quantities to have equal absolute values, the quantities must be equals or opposites. Therefore, we get two equations, x plus 3 equals 2x plus 7, or x plus 3 equals the opposite of 2x minus 7. It doesn't matter whether we put the minus on the left-hand quantity or on the right-hand quantity, but it only goes on one of them. Also notice on the side with the negative, we definitely need parentheses. We distribute the negative on the second equation and solve each equation. We subtract x on both sides of the first equation and add 2x on both sides of the second equation. Then we add 7 on both sides of the first equation and subtract 3 on both sides of the second equation. We can rewrite the first equation to get that x equals 10 and divide both sides of the second equation by a positive 3 to get that x equals 4/3. Thus, the solution is x equals 10 or x equals 4/3.